Let's remind ourselves of what we were discussing last week. So propositional functions have the form p at one or more variables x, maybe x, y, z, x1, x2, x3, where p is a predicate and the variables are unknown. Each of the variables needs to have a domain, which we label u, standing for the universe of possible values for those variables. And the propositional function becomes a proposition if we give values to each of the variables. So we started working through examples. This first one had a simple predicate, x is greater than 0, where the domain or universe of x is all integers. As soon as we give a value like -4, 0, or 4, all of a sudden this now becomes a proposition. We can assign the value of true or false to each of these statements. And then we are working through a slightly more complicated example where we increase the number of unknown variables. Here we have the predicate q with two variables x and y, where x and y can be any real number, and q stands for y equals 2 to the power of x. All that we're doing here is we're plugging in the inputs to that function to the expression y equals 2 to the power of x. So q at 0, 0, that's false. The reason it's false is because we're asking ourselves, is it true that 0 is equal to 2 to the 0? No, it's not. 2 to the 0 is equal to 1. The second one, q at 4 and 16, that is true because 16 is equal to 2 to the 4th. We just plug in the values to that predicate. The third one, this is also true. This one's a little bit trickier. So 0.125, which is also written in fractional form as 1/8. Is this equal to 2 to the -3? Remember, with negative exponents, we would move it to the bottom. So 2 to the -3 is 1 over 2 to the 3rd, which equals 1/8, which indeed is 0.125. Fourth, q at -1 and 2. This is false because we're asking, is it true that, that 2 equals 2 to the -1? Well, we just learned that negative exponents mean we move the term to the denominator, so this is equal to 1/2 and not 2. Okay, and then this last one's a little bit tricky. So q at x and 256, plug in the values. 256, is that equal to 2 to the x? Now here's the thing, this is not a proposition yet. So even though we have passed in some values for the variables, we cannot say whether or not this statement is true or false. Turns out that it's true when we let x equal 8, and it's false otherwise. The fact that we don't know which of those it is means it is not yet a proposition. Okay, we need to still provide a value there. Let's try another example. Suppose I asked you to find all real numbers, x and y. So we could rewrite that phrasing as the universe of x and y is equal to the set of real numbers r, for which the predicate p at x and y is true, given that p at x and y is the equation x times y equals y. Okay, pause the video for a minute and see if you can solve for x and y. Did you get a solution? Turns out there are two solutions to this problem. In the first solution, we can let x equal 1 and y can be any real number. That symbol there stands for an element of. So this is like saying y is in the set of real numbers. And the second solution here is that y could be 0 and x can be any real number. Now, how did we arrive at that solution? I'm going to argue that we could just take this equation and solve it for x and y. What if we were to move the y to the left side? We could subtract y from both sides, and the equation becomes x times y minus y equals 0. And then if we pull a y out of those left terms, that becomes y times x minus y times 1 equals 0. So here is why I arrived at the two solutions I did. if a product is going to equal 0, one of those two terms must be 0. So on the left side here, we could have y equal to 0. And on the right side, we could have x equal to 1, because 1 minus 1 would be 0. Note that when we choose one of those, the other variable can be any value. So if y is 0 and x is 10, this would be 0 times 9. Well, that's still equal to 0. So that's why we have these two cases that we've shown on the left, but note that there's actually an infinite number of instances within each of those cases. We're just solving for the equation and determining what the values of x and y are. Okay, and then in the last example, I want to show you that we can apply the logical operators that we've learned from propositional logic to predicate logic as well. So for instance, suppose we have the predicate p at x that denotes the following expression. The absolute value of x plus 2 is greater than 4. Let me ask you 4 questions. I'll do this first one with you. So the first one says, is it true that p at 2 or p at negative 2? Well, p at 2 is going to be the expression 2 plus 2, the absolute value. Is that greater than 4? I'll put parentheses so we can distinguish it from the disjunction here. P at negative 2 is suggesting that negative 2 plus 2, the absolute value of that, is that greater than 4? You should notice that the absolute value of 2 plus 2, that is 4. It's not greater than 4, so that's false. And then negative 2 plus 2, that's 0. The absolute value of that 0, that's also not greater than 4. So the final answer here is false. Now take a moment, pause the video, see if you can solve for the other 3 questions. Did you figure it out? So p at 0, 0 plus 2 is 2. The absolute value of that is 2. Is it greater than 4? No. So that's false. And I can already tell that this is going to be false because we have a conjunction here and the left side is not true. But negative 10 plus 2, that's negative 8. The absolute value of that is 8. It is greater than 4. But false and true leads to false. P at negative 4. Negative 4 plus 2 is negative 2. Absolute value is 2. Is that greater than 4? No, that's false. We have a conditional. I can already tell you, based on my knowledge of the conditional, that this outcome is going to be true, but it's worth computing the conclusion here. P at 4, that's 4 plus 2, which is 6. The absolute value is greater than 4. So if false then true, that leads to a true outcome. And then the last one here. So we've got p at negative 8. The absolute value of negative 8 plus 2 is going to be 6. So that's true. It's greater than 4. And then negative 6 plus 2, the absolute value of that is 4. That's not greater than 4. So we have if true then false, that outcome becomes false. So I hope you can see how we can combine predicates with propositional logic, and as long as we've provided values for each of the variables, we can assign a truth value to the full expression. That is the basic introduction to predicates. Thanks for watching.